So next one we have the something called the grade compensation. So especially the grade compensation will comes into picture on the curves. So whenever the ruling gradient as well as the change in direction both exist, so the resistance of the track will be increased on this curve, because one thing is the gradient is provided, along with the gradient we have the curves also. During the curves also the centrifugal force will be developed. So counteract that centrifugal force we require additional energy is required. And also if you have the grades also, that may leads to the additional resistance to the movement of the train. So now what we have to do is to avoid to reduce the resistance caused to the movement of the chain, especially at the curve. So though the ruling gradient is prescribed, so sometimes we will limits the gradient what it is being provided. So the gradient what we provided will be still steeper than the ruling gradient what it is prescribed. So you can see here in the picture it is given, you can see, so this is the actually the how much gradients that need to be provided from we'll take point A, B, C. So from B to C, that is what the gradients need to be provided. But at the curve, since the resistance will increase because of the combination of the both gradients and the curves, the radius of the curve which has been provided, the gradients will be slightly reduced. So we made the gradient little steeper. So now what is the amount at which the gradient has been reduced? That we call it as the grade compensation. So from B to C, that's the ruling gradient or the maximum gradient what is to be provided, and I'll take this point D. So but this is the gradient from B to D is the actual gradient what it is provided at the curve. So because to reduce the resistance that is caused for the movement of the train at the curves. So now what is the amount at which the grade has been reduced? That we will call it as the grade compensation. So how much that need to be compensated? So that depends upon the type of the track, and it is given as for the BG track we need to reduce the gradient by an amount of 0.04 percentage for every degree of the curve. Okay, the radius of curve may be 2 degree, 3 degree, 4 degree, 6 degree, it can be anything. But so the grade compensation what is given by the standards is for every 1 degree of the curve how much that need to be reduced. So similarly for meter gauge track, the grade compensation should be 0.0 percentage per degree of the curve, and for the narrow gauge track the gradient has to be decreased by an amount of 0.02 percentage per degree of the curve. So we'll take up one example on this grade compensation, and we'll look how the actual gradient will be provided on the. For the broad gauge, if you have a broad gauge track, the grade need to be compensated by an amount of 0.04 percentage per degree of the curve. So here the example here, this says that the ruling gradient is 1 in 150 on a particular section of broad gauge track. At the same time, we have a curve of 4 degree which is situated on the ruling gradient. What should be the allowable gradient? So now they are given, we have the value of ruling gradient is given as 1 in 150 is given for you. But they say that there is also a curve of 4 degree. So now whenever there is a combination of gradient as well as the curve, we have to slightly reduce the gradient what it is provided. So that is the grade compensation. And now they are asking to calculate what is the actual gradient that is provided. So first write down the data that is given for you. Ruling gradient is 1 in 150 and given it as a broad gauge track. So now for the broad gauge track, what is the grade? So consider that as per for the broad gauge track, so it need to be compensated by an amount of 0.04 degree percentage per degree. So now for us we have the radius of degree as 4 percentage. So 4 into the prescribed grade composition. So here the actual what it is, the gradients what we have, that need to be reduced by the 0.16 percentage. So the ruling gradient is given as 1 in 150, convert that into the percentage, because now the grade compensation we have it in terms of percentage. So first the gradient is given in terms of 1 in n. Convert that into the percentage first. Vertical divided by horizontal multiplied by 100. So how do you convert vertical in divided by horizontal into 100? So that will convert your grade in terms which is there in the 1 in n to the x percentage. So now the percentage gradients what has to be provided is 6.65 percentage. So now this 0.65 percentage need to be reduced by an amount of 0.16 percentage. That's a grade compensation. So actual gradient what has to be provided will be equal to the total gradient 0.65 minus the grade compensation, that is 0.16. So actually we have to provide a gradient of 0.151 percentage. So or this is expressed in terms of percentage, convert that in terms of 1 in n. So how do you convert 0.51 divided by 100? So you can convert here 1 divided by 100 divided by 0.15. So that will give 1 in 196 is the actual gradient which is provided at that particular point where the combination of grade and the curve exists. So you can see here actually the ruling gradient is given as 1 in 150, but we are providing still the steeper gradient to overcome the resistance that is caused because of the combination of the gradient and the curve. So here you take up another similar example. Here we have a broad gauge, the same thing, the actual rolling gradient need to be provided. So the information what they have given, the rolling gradient is given as 1 in 200 on a broad gauge track. Once again the curve, the degree of curve is 3 degrees superimposed on the above track. So the grade compensation is, what is the grade compensation for broad gauge track? At 0.04 percentage per degree of drag. So now we have 3 degree curve which is situated and that gradient. So 3 into 0.4 will get around 0.12 percentage. So the ruling gradient what they given is 1 in 200. Convert that to percentage. How do you convert? Horizontal divided by vertical multiplied by 100. So we will get 0.5 percentage. So this is the total gradient, the ruling gradients that is provided and the grade compensation. Okay. So now the actual gradient will be ruling gradient minus the grade compensation. So that will gives you the actual gradient to be provided, 0.38 percentage. Converting that into the 1 in n type, so we will get the gradient to be provided as 1 in 264. So this is how you can calculate what should be the actual gradients that is required to be provided when you have the combination of both the gradients as well as the curve at any location of the track section. The next geometric components what we need to consider is the speed of the train. So what is the speed of the train achieved depends upon the strength of the track as well as the power of the locomotives that has been adopted in pulling the train. So and also if you use a diesel traction and the electric traction, higher speed of the trains can be achieved. And anyways, with the modernization of the Indian railways and the construction practice and use of electric traction, we can achieve the speed up to 150 km per hour in the BG track, and in the meter gauge track the speed can be achieved up to 100 kmph. So these speeds are in the straight track. Okay, so what is the speed, and also when it comes to the curves, what is the speed of the train achieved, that depends upon what is the gauge adopted at the curve and the radius of the curve, rate of super elevation is provided, and the presence and the absence of the transition curve. So next, how to determine the speed of the train at the curve. So to determine the speed of the curve, we make use of Martin's formulas. As I already mentioned, the speed on the curves depends upon the various parameters, which includes the speed and the rate of super elevation provided and the gauge of the track. So now in the Martin's formula, we will get the speed relationship between the speed and the radius of curve will be given. And for considering the radius of the curve, what should be the speed achieved by the trains? That is given by the Martin's formula, and the speed also calculated considering the rate of super elevation provided and the presence or absence of the length of transition curves that has been provided at the curve. The speed is calculated depending upon the various consideration, and whichever comes minimum, that speed will be adopted by the trains. So now we'll look into that how the speed can be calculated with the help of the Martin's formula. So to determine that, we have three conditions. The first condition where the transition curve exists, the second curve where the transition curves are absent, and generally for the higher speed. The first two conditions will gives you the relationship between the speed and the radius of curve up to a speed of for the lower speed. So first thing is, when the transition curve is absent, and the speed can be calculated in the BG and meter gauge track as V is equal to 4.44 square root of R minus 70, or you can calculate this as 4.35 square root of R minus 67. So similarly for narrow gauge track, the speed can be determined with the second equation B. Okay, and these equations are valid, the relationship are valid only up to a speed of 50 kmph. If this train speed exceeds more than this, we cannot use this formulas. And similarly, if the transition curves are absent, so now the speed value has to be decreased by an amount of 4/5 speed of the what is calculated for the in the presence of the curve. So that value can be taken as 4/5 of 4.4. The value is reduced to 3.52. Okay. So similarly for narrow gauge, it can be taken as V is equal to 4/5 of the previous formula B, 3.6. So that will gives you 2.92. 3.65 into 4/5, that will comes to the 2.92 value. And the speed restrictions here, the formulas will be valid only up to a speed of 40 kmph. And now for the higher speed, the speed is great. If the speed of the train is greater than 100 kmph, we can use the general formula as V is equal to 4.58 into square root of R, where R in all these formula refers to the radius of curves in meter. So this is how we can determine the speed of the train at the curves. With the condition, what is taking in the view of radius of the curve. So anyways, how to calculate the speed value depending upon the super elevation and the transition curve, so that we will further discuss in the coming sessions. Thank you.